All right. Well, let's go ahead and get started. And so please chime in with, there have been a few questions, but please ask your questions, and probably would recommend you do it in Slack if you can. If you don't have access to it, chat's fine, but just for the sake of everyone seeing your questions. So what I'm going to do now, well, I'm going to spend a couple of seconds just trying to summarize where we are and what I think the important takeaways are. The first big takeaway, which we've been exploring, is that 5G is undergoing some significant changes, and going faster is the least of it. We're moving from a world where both the base stations and the packet core were closed, proprietary. They had evolved over the decades out of what had originally been a voice service, incrementally adding IP-ness to it over time, but now finally going completely in the cloud direction is the big thing. And so what we saw is that we take what was typically or historically been bundled in the base station eNode B in 4G, and we're taking pieces of it and moving it into different places in the network. And that packet core, which it was called EPC in 4G, and there are open source 4G cores, absolutely, but they were basically a bunch of legacy code dumped into a VM. It's not been necessarily the best world, but what's happening now is that those functions are being re-implemented, and I wouldn't claim that we're there yet, but the open source versions of this are adopting microservice-based architectures and designs, and that means everything microservices is supposed to mean. You have stateless microservices, you have a shared data store of some kind, key value store, and everything's supposed to scale horizontally. The code that's out there today isn't quite there, but that's where it's rapidly heading. So this, the big summary is that all of these parts, with the exception of some of the stuff going down in the RF end, are open source, microservice based. We talked about several of those pieces already. Not all of it comes from ONF, by the way. There's open source, open air interface. OAI has an open source down here that is really important. And there's other people that have different cores as well. Magma is another core that's out there. But I'm approaching this from the point of view as some pieces that I know fit back together again. So that's going to be what I'm going to describe. Here is the big takeaway. The line between where the cloud lives and the access network has been way back to the right. What this is all about is that's moving. Maybe if you wanted to think of the radio as the access end, fine. Maybe that's where you're interested in. That's great. But just the cloud is, software is eating the world. Software is eating the access network, and it's most certainly eating the mobile network. So these are all going to be in the cloud. And the second they're in the cloud, no matter what they looked like when they became cloud services, they will evolve and become increasingly cloud native, and you're going to manage them in cloud native ways. And you're going to deploy them in ways that are not the conventional telco dominated way of deploying this. You can deploy it in your enterprises, for example. So if there's one slide to take away, there is an opportunity here to bring best practices in cloud and research and how these things get reimagined as cloud services. We're not done though, because it's not just that it's going to be the cloud, it's going to be the SDN cloud. So we're going to take the control plane out of the central unit. It's not going to be a black box or a red box. It's going to be an SDN controller called a RIC, and it's going to control all the other pieces. And we're going to populate it with X apps or control apps. This question came up, what are the research opportunities? This is all open space here because, like I said earlier, There are solutions to some of these problems in the 4G land, but as soon as the radio has the capabilities that the 5G radio has, these are going to prove to be inadequate very, very fast. And by the way, another question that came up, just to sort of tie it back in, there can be multiple cores. The second these are cloud native, then they're going to become specialized, and there's going to be a subset that are really good at high bandwidth streaming, and there's going to be another subset that's going to be really good at IoT, where you have low powered devices. So you can get, it now works to have multiple implementations of the core, each tailored or customized for a different kind of traffic behavior, just because you can now, and then therefore you optimize it for the use case. On top of this, there's still a management plane. That's where policy is going to be set. There was a question about management planes. There's a whole lot of language out there from the telco world about management planes, but don't forget, this is now a cloud service. This is going to be a cloud managed service, and all the best practices in how we manage cloud services, including the agility of DevOps, is going to become part of that equation. And so I would argue it's probably not going to be yesterday's management plane. Again, opportunities there. But if you drill down one bit lower, what we see is that there's going to be 3 control loops. And every time there's a control loop, there's going to be an opportunity for doing research there, I believe. So there's the non-real-time control loop that sets the policy. There's the near real-time control loop that is telling the RAN units what to do. And then there happens to still be one real-time control unit running in the DUs. That's where the scheduler lives. That's sub-millisecond. This is tens of milliseconds, and this is on the order of seconds. So there are 3 different control loops at different granularities. Then we can go down into the data plane and find opportunities to implement the functions that are actually passing packets back and forth in P4. I only had P4 point to the CU data plane, but you could have the P4 point to these as well. These could be implemented in P4 in principle anyway. So the UPF, there are multiple actually demonstrations of how you can implement UPF in P4 in a programmable switch. This is a tougher nut to crack because there is state. And so, well, there happens to be a fair amount of research going on right now in how to generalize what you can do in P4 so that you can implement other network functions. I could imagine you could push that in a direction that supported the kinds of functions in network functions that something like the CU user plane needed. Segmentation reassembly is happening over here. So sort of the same idea. So again, opportunities. So what I'm going to do is spend a little time talking about how all of these parts have been assembled into a platform called Aether. It's a managed service for enterprises, and from where it says enterprise, you can read your campus. It's been deployed on several university campuses. It is an ONF project, but it's being built out as this ONF's nature. They're working with a lot of companies in the industry. So there is, I'll point out later, Deutsche Telekom and a whole bunch of vendors at ONF have a deployment planned within the next month or two of all of this in a real world setting. So this is the platform. Now, I'll talk about the platform, then we're going to come back and talk about research opportunities on that platform and ones that my colleagues have been working on. Okay, so this is where just a summary of a slide that you saw earlier. It's kind of the overview of what Aether does. Again, in the central cloud, literally it's in Google Cloud. There's a control and management platform. This is Aether's version of a management plane, but it's built in cloud style. The user plane of the core runs in the cloud. I'm sorry, the control plane of the core runs in the cloud. The user plane of the core runs on the enterprise. The entire SD-RAN runs on enterprise. Again, that blows up into the controller and all the apps. There's a set of edge apps and a set of central apps. So that's the high level picture of what Aether does. And again, that gives you local breakouts so that all of your devices can talk to the local edge apps without ever leaving the enterprise. It clearly has bandwidth value. It also has security value because you don't, in many cases, you don't want your data to go off enterprise, off site. So Aether is built out of commodity hardware. I flipped the servers and the switches. Don't let that confuse you. I just did it because the software running on the servers running on top. So the first thing you run here, I'm sorry, the hardware also then connects, one of the leaf switches connects to some number of small cells in your enterprise. So this is literally the hardware configuration. You can build it out smaller or bigger. I'm kind of just showing a generic version of it here. I think that most of the deployments we have 5 servers and 4 switches and 1 or 2 small cells attached to it. We load some of the basic underlying platform. You've got to control the switching fabric. So we load ONOS and the SD Fabric app on it. And excuse me. And Stratum then runs on the individual switches. Then we work, this is now a cloud. It's Kubernetes managed. I probably got to say that. Kubernetes is managing the switches. It loads some of the software onto the switches. It certainly loads the software into the microservices running on the servers. SD-RAN is a set of microservices. It includes the ONOS RIC and the set of edge apps, XApps. And the core includes the user plane pieces of the microservice implementing the user plane pieces of the mobile core. I'm not showing the data plane or the control plane because it lives off site. That's just one site. So we call this an Aether connected edge. And that can scale out to multiple edges. One enterprise can have multiple edges or multiple enterprises, each with one edge. The next piece then is that we need to manage that, and it's all managed from a central cloud. There can be multiple instances of the core running in the central cloud. And again, I mentioned the motivation for that. It's largely a matter of isolation. If you're carrying traffic on behalf of different enterprises, they may insist that their cores be distinct. But it also gives you the opportunity to not only give different QoS properties to each core, SD core, but also customize those cores for different use cases. So you're not stuck with a one-size-fits-all core. And then the last piece is the Aether management plane, which we call AMP. This is the cloud counterpart to the orchestrators that you might find in other documents about how to implement this. So what I want to do is, well, let me just, stop and emphasize. These are open source projects. You can get access to the code, and then you can change the code and do what you want with it. But it also then comes deployed on a set of sites managed by this managed service suite that I'm talking about here. So what I want to do is I want to blow this up a little bit, and I'm now going in the management direction, but it doesn't matter how much open source software you have if you can't deploy it and operate it. It just sits in GitHub. And we don't call them network operators for no good reason. Operating the networks is the hard problem. And while a lot of hard work has gone into disaggregating this and building up the software, the management of that software and the operation of a network is ripe with challenges. So let's blow that up. If you look in pretty much any cloud managed service, this is managing connectivity as a service. You're going to find the same basic components, whether you're managing connectivity as a service or rideshare as a service. You still have to solve many of the same problems. And these may not be quite as familiar to this community because they're more from the cloud side, and it's also SIGCOMM doesn't go into the management plane all that much, but I'm going to spend a little time here. So you have to monitor and log information from down in the system, the cloud services you're managing. There's runtime control. I have to change parameters at runtime that, as subscribers come up and down, and I have to manage the QoS that I give them and so on. I'll show you an example. You do lifecycle management because the software is not static, it's constantly evolving. And this is where the entire agile programming DevOps comes into play. We're going to continuously deploy new software. And then you have to do resource provisioning, which is kind of the bootstrapping step to get the hardware up and running the first time. But then over time, I come and add more capacity, and I have to provision that capacity so that it fits in and starts playing nice with the rest of the cluster. So from right to left, monitoring logging is an essential component. I just took a screen. This is just a screenshot of different data that's being connected. This actually was snapshotted on the 4G version instead of the 5G version. So that's an MME. That's just yet another acronym that we don't have to worry about. But there's stats on subscribers, there's stats on bytes transmitted and received, and so on. The point that I want to make, though, is this entire system is built from open source. So if you are not familiar with these particular projects, these are all combination. I think they're mostly Apache, but a combination of Apache and Linux Foundation projects go into this. Prometheus is a time series database. Grafana is a graphical interface on top of that. Elasticsearch, Kibana, and FluentD are all components to collect, archive, and search and display logging information. So this entire logging and monitoring system was built from open source components. It's just a matter of getting them all to fly in tight formation and do all the configuration management for it. So that's monitoring logging. Runtime control is a programmatic API and a graphical portal that you expose to the customers that are using this service, that have it deployed on their campuses or their enterprises. It lets you manage device groups, devices. It lets you define the slices you want to isolate traffic and define the QoS parameters for those slices so that they get the data plane behavior that you want them to. And it does the binding between device groups of devices and applications mapped onto slices. So again, slices deliver isolation and QoS to a set of apps and device combinations. Again, this is just a quick and dirty screenshot, couple of screenshots showing you the kinds of things that you can come in and control from the runtime control interface. So everything having to do with devices and applications and slices is controlled from a GUI. But there's also a programmatic API. So here's the next opportunity. I'm just replaying the picture I had of before. You see the portals up there? Well, there's also a programmatic API. So I can put closed loop control apps on top of the runtime control system and the monitoring system. I can collect data, do analysis. If that's machine learning, great, whatever your analysis is. And then I can close the loop and change the control. I've got all the knobs, gauges that I can read and knobs that I can set. This is fertile ground for work. And I mean, this whole loop is, on the monitoring side, I'll let Jen talk about it later, but having the right databases to store all this information and zoom in and out on it and do queries is an interesting problem. And so just because we have a first cut solution doesn't mean that we're done there. You will see examples, and Jen and Nate will talk about examples of doing closed loop control, turning around and controlling the network after you make observations about what you've seen. Lifecycle management is a topic near and dear to my heart. It's one that's quite often ignored in the research community, but I think it's an incredibly interesting one and an incredibly important one. Sometimes called continuous, the gold standard here is continuous integration, continuous deployment. So what you see in this picture is the developers or the researchers are innovating and they're checking code into a code repo. You continuously integrate that code and you produce images, Docker images, And then when there are new images, you continuously deploy them out into the operational cloud. And another piece of input to the deployment is that you've got, how that cloud is configured. So we've got, if you've heard of infrastructure as code, that's basically a repo that has code, typically declarative specifications of what my infrastructure looks like, so that I know how to deploy the software to all of the places it needs to be deployed. Again, this is 100% open source. You were here in the sense that you can check code into this pipeline as well as anybody else can check code in this pipeline. And that code will ultimately be deployed on the Aether pilot deployment. You're checking your code into GitHub. I'm sure you're familiar with GitHub. You may not be familiar with Garrett, which is a wrap around GitHub that lets the other engineers have an opportunity to inspect your code and approve it or not. That's all part of the process. And again, both it's the code and the configuration state that's checked into repos. The common intermediate representation of everything that's between continuous integration to continuous deployment is there basically a bunch of Docker images, get uploaded into Docker Hub and then downloaded into deployments. Helm, if you're not interested in, is basically a way of specifying what set of Docker images I want to compose together. The integration system is based on Jenkins and a whole bunch of testing frameworks to test the data to make the code to make sure it's okay to integrate it. And the deployment are a couple of systems called Rancher and Terraform. These are all open source. There are proprietary versions of a lot of this stuff. One of the most active areas in the cloud world right now is to build this and offer it to you as a service, because the cloud folks understand that people are starting to deploy more workloads to their edges, and they want to manage the lifecycle management of those edge clusters as though they're just extensions of the cloud provider's data center. But there's no magic here. This is entirely open source. It's just a matter of gluing all these parts together in a coherent and meaningful way. So on the right-hand side, there is an operational cloud, and every time code is checked in here and it gets integrated, we don't necessarily instantly, it's not continuous, doesn't mean instantaneous deployment. We have test staging clusters that code will get run on, and then we'll open the gate and let it go through to the production network. There's all kinds of gating functions in here. You have to pass a set of tests to get to the integration phase as well. And like I said, Aether has been operational for going on 2 years. You can see some of the sites here. The blue is all of the management software is running in Google Cloud. We have multiple ONF sites, Intel, some of our corporate partners, and you'll see Cornell, Princeton, Stanford as well, using it within, installed Aether pods and doing research on it. So before I take it the next step, let me just see if there are any questions. I don't have the Slack in front of me, but maybe if there's something that needs more attention, I'm happy to do that.
Nothing new on Slack right now.
Okay. I don't have a link in here, but if you go to the ONF website, if you are interested in having a cluster running at your university, step one is to become a member of ONF. That's for free for universities. This is being streamlined. We've for the sake of universities doing that, but we can then get you connected. There's a bill of materials to bring up various clusters and then get them up and running.
Larry, there's a question on the Zoom chat. Can Aether be easily installed as a standalone testbed?
As a standalone?
As a standalone testbed.
So yeah, I mean, for development purposes, we have the ability to bring up both the Aether pods, the edges, and the management plane on a laptop. All right, so you can take variations of that. And that's just for development purposes. You have to have your own little sandbox management plane. There's an important distinction though between Aether as a managed service, which I'm talking about here, and Aether, the software stack. What we have done with Princeton, Cornell, and Stanford is they have actually 2 pods running. One is quote unquote in production and the other is a development pod. We collaboratively work on keeping the software on those up to date. So Princeton is not doing management of their own cluster per se, but they have a development cluster that they do their work on. Could you do that entirely standalone? Yes, you could. That's not, there is some work to make that trivial because bringing up the management plane is something that our ops team does right now. And that's a pretty substantial lift. There's a lot of pieces to that. It's all managed in the same lifecycle management. So in principle, it should be just as easy. It's just not something that we have a lot of experience doing. So you may have missed the last little thing here. There's an outdoor field trial with DT, Deutsche Telekom, and a bunch of different vendors in the ONF software all coming together sometime in September or October. That will be a pretty significant demonstration of all this in the wild. Okay, so now we're ready to transition to the research opportunities. And before I hand the floor over to the others here, I'm just going to paint a little bit of a picture of what this space that this group has been exploring. And by no means is that the only interesting space here. Hopefully you've seen some of the other possibilities called out. The project is called Pronto, and the title of it is Securing the Internet Using Verifiable Closed Loop Control. It's end-to-end, and as opposed to just looking at switches or just leaf-spine switching fabrics, it also includes the 5G piece. So this doesn't sound 5G centric, but 5G because it is an important part of the end-to-end path. But this is about how to bring closed loop control to not only the switching fabric, but also the SD-RAN. And we're all partners in doing that. And it runs on, like I said, it runs on Aether. So this is Aether, 1 pod's worth, and I'm just showing the edge pod. I'm not showing the management plane here. And so what basically is happening is we have, through the use of in-band network telemetry, we are able to instrument the switching functions, fabric.p4, if you remember from earlier, running on all these switches here, and collect telemetry data. And then we feed that telemetry data into a verifier that is comparing the observed behavior of the network with the original specification that we were given as to what the network was supposed to do. And we were given that initial specification because the forwarding plane is implemented in P4. So we know what it's supposed to do. We told it what to do. I'm not going to say much more because I want to make sure there's plenty to talk about for Nate and Jen and so on. But that's the basic idea. And then having, you may verify that everything's behaving exactly as you intended it to, but you also might find that it's not behaving the way you intended. And you have the opportunity to control the loop and go back and control the system. And it turns out that one of the ways that you do that is you change what's running in the, well, I referred to it as SD Fabric ++ here. It's both controlling what's running in the switches and controlling the control app that's running up in the control plane. So it's both data plane and control plane related. That's the general idea. We have a particular set of demos. I'm not going to show the videos, but the links will get you there. Where basically we went into a Stanford aerospace lab, set of drones flying. It's pretty hard to wire drones, so they're communicating using wireless back to the small cells that we have deployed, running this software stack. And an edge app, which is drone control. So drone control issues instructions to the drones. The drones fly in formation. This is a really great networking demo because unlike any network demo I've ever done before, you see ping print out some message and then you say, look, it did what I told you it was going to do. In this case, if we don't detect the problems and correct them, the drones, well, it would be great if they actually caught fire and crashed and burned, but that's not what happens. They just land safely because we don't want to have to replace them. But you get to visually see the impact of the attacks and the impact of the remedies from the drone control. Now, you could have controlled the drone remotely with a remote human flyer, but what we're doing is we are closing the drone control loop and we're doing motion capture because the room that these drones fly in is instrumented with a set of cameras. They all ship video back to the edge cloud. Motion capture happens. Instructions or the consequences of motion capture goes through the switching fabric and comes into drone control. Drone control decides what to do. Again, instructions to manage that go down into the switching fabric again and out to the RAN. So there's all kinds of opportunities for collecting and looking at and doing verification that the behavior you expected is what you're getting. So with that little bit of an intro, I'll just point you at all of the links that you can get to if you go to the page that has all the links on it. And let me, we'll transition now, and I'm not quite sure how this is all going to go, but let me initially, I don't know, Jen or Nate, do one of you want to go first?
Yeah, either of us could.
Either way.
All right, and my screen, Jen is on the first one, so I'll let her go.
Great. Okay, thanks, Larry.
Now,
So-
if you want the screen, you can have it.
No. In fact, why don't you just go to just turn off screen sharing? We can just all move into a more discussion-oriented mode. That'd be fine too. Awesome. So first of all, thanks, Larry, for the overview. First of all, I've been really excited about this area as one for research because I've been interested in wireless for a long time, but never quite sure if the things I knew how to do were useful in that space. And the framework Larry lays out really shows a lot of opportunities, I think, for networking researchers to contribute. And so I've been looking at this in three main ways. One is an opportunity to view the 5G network as just an amped up use case for things I'm already doing, where now the latency, reliability, and security requirements of the applications that connect to the network are just so much more severe than they were before. And so some of the demos that Larry just talked about are a good example of that, where we took techniques that we've been looking at in data center and backbone networks for telemetry, for measuring problems in the network and mitigating them quickly. And they just become all the more palpable in a setting where a real-time application like multiple drones flying in formation really make it clear that you need to have that network control loop close really quickly and automatically to make those applications work well. Now that's interesting, but doesn't grapple with the unique characteristics of the medium in a deep way. And so a second category of work we've been looking at is trying to make the 5G infrastructure itself more scalable. And Larry alluded to that earlier in the work on the user plane function. And we're generally looking at the user plane function and also the sort of border firewall NAT, if you will, that connects the access network to the core to make those better scalable and better able to take advantage of programmable network equipment in service of that greater scalability. And then a third category that's sort of really early days for me, to be honest, is looking at emerging applications that now grapple hopefully in more interesting ways with the fact that it's a wireless access network. And there I'm interested in three things at different levels of maturity. One is video applications, in particular, optimizing video quality of experience for video conferencing over 5G, and also having the network help support multi-camera analytics kind of scenarios where there's a high volume of traffic coming from a bunch of network attached cameras where the network can play a role in helping the analytics application scale better. And then second, looking at the idea of a privacy slice in the 5G network where you might be able to provide additional anonymity and protection against fingerprinting for users that are connected, have their traffic connected to a particular slice. So here you're trying to protect the user from surveillance, let's say on the wide area that might otherwise have their traffic revealed or their identity revealed or their location revealed. and trying to have in-network services to protect that. And then finally, Larry mentioned drones, and I'm interested still in understanding some other use cases with drones that better optimize how we provide security services to mobile devices, including drones and other UAVs, where a security footprint may need to move along with the mobile device to continue offering continuous protection of it as it itself moves from one base station or even one mobile core network to another. And those are just a few examples. All of those are in very early stages of work, so I don't have anything more concrete to say than that.
So can I ask you some questions?
Of course.
So just thinking of various touch points that have happened between the students and the engineers. It's been fun to watch, but in-band network telemetry comes with its own set of databases. Aether comes with a set of databases, the time series databases and so on. And I know you and your group have worked on how you represent all the data and keep tabs on it. Could you say just a tiny bit about that? Yeah,
definitely. So at one extreme is that we do the telemetry, the collection, analysis, and adaptation completely in the data plane. And that's sort of a first step. And for a class of applications, that's sufficient. If you can do everything, for example, in P4, you might be able to put all of those steps of collecting, analyzing, and acting on the data in the data plane. And that's what we've done in the first step. But things get a lot more interesting if you want to do more sophisticated analytics where the switch is not capable alone of doing all of it in the data plane, or you want to contribute to a larger network-wide view. And so we've been trying to develop a more general telemetry feed that we can feed into ONOS so that we can do at least some data reduction directly in the switch, but then provide aggregated statistics of interest back up to a higher level control application that might be acting in a more network-wide way or doing more sophisticated analysis than you could reasonably expect a hardware data plane to be able to do. And there, I think we'll be integrating much more tightly, with the ONF software stack to enable that to be integrated with the other forms of data collection that you alluded to earlier.
Thanks. Are we heading off to Nate?
I think so.
Don't be shy with your questions or comments.
I'll have to use an old joke of my PhD advisor, which was, the way to get questions is to speak not very clearly, and then people will be confused and ask questions. Jen clearly speaks way too clearly. So I think, Larry in his introduction to Aether and Pronto really highlighted how open source is kind of one of the key kind of North Star guiding focuses, and also programmability. This top to bottom end-to-end programmability. So if you think about programmability, I think it really gives you two things. One is visibility and the other is control. And at least in the SDN community, I think we tend to focus on control. If I have the ability to program the control plane or the networking elements, what new things can I do? What new programs can I run? But obviously visibility is also really critical. It's hard to think about what kinds of programs you might want to write, what kind of control loops you might want to have if you don't understand what the state of the network is. Most of my work on the Pronto project has been looking at how the visibility, or the ability to observe that we get from programmability allows us to do new forms of reasoning and formal verification. In particular, if we have systems built in the way that Larry described, as modular components, each with interfaces between them that are defined in software where we can understand their meaning, then we can start to reason about them, and we can start to deploy techniques for verifying them. So I'll briefly talk about three thrusts that are going on in my group connected to the Pronto project that sort of fall into this theme. So one is we're building verified implementations of P4 data planes. So this is a project called Petra that was published last year in POPL. We have a GitHub page that you can look at. And really what we're trying to do is kind of nail down exactly what the P4 programming language is. What is its syntax? What is its semantics? What is its type system? And the sorts of questions that programming languages researchers kind of obsess about. Now, why is this important for networking folks? Well, P4 is by now a pretty mature language. It's got, there's companies that are building products that can be programmed in P4, and there's open source community that's evolving the specifications and open source software around it. But if you want to have kind of assurance about the correctness of systems built around P4 data planes, it's really important to know what a program is going to mean. In other areas, like in ISAs for hardware chips, or in low-level languages like, say, WebAssembly or Rust, there's efforts that have applied a very formal approach to defining their semantics. And these formal language models really sit at the bedrock of verified systems. So we've been applying sort of the same methodology to P4. And in the course of doing this, we've produced some artifacts that I think are useful for folks who want to build verified network systems. We've got a reference interpreter. We've got mechanized versions of the semantics of P4 that are written in the Coq proof assistant. So you can sort of run programs, and you can also do proofs that are checked by a computer about properties about P4 programs. And we've also, as a kind of design aid, we found the task of going through and formalizing the semantics of P4 to be very useful. It kind of forces you to answer all the questions about the kind of dark corners of the language or weird, tricky cases. So that's one effort, is just kind of putting P4 in a solid foundation. And just to say where we're going in the future, right now we're working hard on building not just reference interpreters that adhere to this formal semantics, but actually efficient implementations. So for example, a software data plane where you can feed in a P4 program, compile all the way to x86, and get an end-to-end proof that the x86 code is the same as the original P4 code. A second direction is runtime verification. So there's been a ton of work on network verification in the SIGCOMM community over the past 5 to 10 years. There's a whole session at the conference. I think the very first session is on network verification. And a lot of this is exploiting the opportunity that programmability gives us, right? If we have programs that define the meaning of the network, we can start to reason about those programs. But most work, not all, but most work to date has been about static verification. So if I go back to the early work on SDN verification, there were several folks, the Veriflow team, Anteater and Veriflow at UIUC, and the folks at Stanford in Nick's group, and became Forward Networks, and several others that realized that if you have OpenFlow, which gives you a programmatic interface to the data plane, you can intercept the configurations that are coming from the SDN controller and start to statically analyze those. It's not really static, actually, because the controller, of course, is continually changing the rules that it pushes down, but sort of in each snapshot, you get a view of what the network's supposed to be, and you could check if that configuration implements the policy that you want. Does it correctly enforce access control? Does it provide connectivity? Is it free of loops, and so on? So these static tools are really cool, and I think there's still lots of great work to be done. And in fact, folks have extended this, making these tools very fast, extending them to control plane configurations, looking at fault tolerance, lots of stuff. But there's a direction that I'm interested in, which is runtime verification. So the idea here is not to do any kind of proof, before the network software has been pushed down to the data plane that it's correct. But instead to instrument the network program so that it enforces the properties we're interested in. So one of the demos we did for DARPA that Larry pointed to, if you go to the Pronto webpage, you can see one of our videos was taking properties like, data should not be exfiltrated along certain paths, or sort of a simple characterization of denial of service traffic should not be allowed to get through. So we can take these properties and we can actually compile into the network runtime monitors that enforce those properties. So the idea is to essentially instrument the behavior of the network, generating a sort of trace of what's happening, and then have enforcement code that prevents, in the case of, say, a safety property, a bad thing from happening. And the prevention can take several forms. We can drop packets that are about to violate the property, or we can send them to some kind of auditing service or the control plane to take further action. So what's cool about runtime verification is, first, it's operating at a very low level. Unlike static verification, where you're taking some model of what the network should be doing, whether it's a model of BGP or a model of an SDN control program or a model of OpenFlow, and then building a mathematical model and efficient checking tools for that model. Here, we're actually compiling code all the way down to the low-level data plane. And that sort of cuts out a whole bunch of things that we have to trust. We don't necessarily need to know that the models are being completely faithfully implemented. We just need to know that the checking code is there and is running correctly. Another reason I'm excited about it is it sort of directly connects up to all this work on telemetry that Larry alluded to, and potentially on sort of properties that go beyond the kind of simple path properties that most verification work is focused on to date. So looking at stateful properties and looking at quantitative properties where you're talking about not just a single packet and the path it takes, but a whole traffic aggregate. These are things where the technology to do them is known in the runtime verification community. So it seems like an opportunity to bring it to bear here. And then one third area I want to quickly touch on is what I'm calling causal telemetry. So if you look at what's going on in the distributed systems community with distributed tracing and observability, there's sort of a rich academic literature and tons of startups that are building, debugging tools that give you much more information than what we have in networks today. So in a very early stage project, we're looking at how we can, again, exploit programmability to let us collect the same kind of fine-grained information. Not just about a single packet and where it's gone, but potentially about the whole distributed system that makes up the network. And there's lots of things you could do with this. You could use it to do kind of anomaly checking and verification. You could use it as a debugging tool to look at performance problems. We're still exploring some of those. And we're also interested in looking at what happens when you have the ability to collect this kind of observability, both in the network fabric as well as at the application layer and maybe in the radio network. I think there's some synergies there. So I'll stop there, but the kind of, just to bring it back to where we started, I guess my real interest, like Jen's, is I've been curious about wireless networks for a while and mobile networks, and it's pretty clear that there's this big transformation that's in the middle of happening, and it's really exciting to me that folks like Larry and Oz have kind of taken the systems approach and kind of SDN principles and come up with a rational way to understand the 5G cellular access network through that lens. And I'm really interested in how we can use the visibility that we get through programmability to do reasoning and build networks that are ultimately more reliable.
Thanks, Nate. Just looking to see if we have questions here. Jumping between Slack and chat.
I'd be curious, like, if I could ask you a question. What do you and also Oz, what do you guys think are the most interesting research questions here?
So Oz is on another call right now.
Oh, okay.
Yeah, so I like we all have certain flavors of systems questions we like. I like understanding where the boundaries are, how to craft boundaries on platforms so that you can support as many use cases as you can. So that's partly about, just trying to find that sweet spot and the abstractions that capture what the platform offers. And so I think there's a host of those, and I tried to call attention to that. There's an important boundary here, and we don't have it down yet. And so there's a whole class of problems like that. The next class problems are, all right, there seems to be some consensus about where some of the boundaries are and how to factor things. But suddenly the workloads have changed on us, and we have a whole bunch of optimization problems we have to start thinking about. Excuse me. I think at the end of the day, a lot of the interesting things that happen will be driven by the applications that people suddenly understand. Oh, I think I could do that, and then that drives it. So we kind of explored that space a little bit, and a lot of the early applications that people talk about are running cloud apps on the edges and then make them they're better because they're closer. That's great, but that's not as interesting as there are things that I can do now that I just could not do before. And so the whole creative end of the app space, I think, is a great one. I don't know what those apps are just now. I mean, the way that I approach these problems is I like to have a demonstration up and running and start to play with it, and then figure out where my points of pain are. Yeah, it's a very general answer, but how we factor things, how is the data collection? We were talking about data collection. How is data collection factored between sketches collected in the data plane, some slightly more granular snapshot on the switches, something even larger aggregation collected back on the servers? How is that factored into the control like ONOS?
Yeah, there's a question related to that in the Slack right now, asking about what kind of data you can collect from the RIC, and in general, what kind of telemetry can you collect on the RAN side that could perhaps be combined with some of the things you just mentioned.
Yeah, that's a great question, and I don't have the schema for that. I haven't looked at it in a long time, so I'm kind of going from memory here. But I think if you go back to the notion of the channel quality indexes that you're getting back, that's all available to us. So, and I can't give you precisely, but you're based to a first approximation. You are learning about the signal quality being delivered to the UEs, and that's what you get reported back. That's immediately available down in the DU, but aggregations of that are being passed up because you have to have that to make the spectrum allocation decisions. So, I mean, I've heard people talk about how to take advantage of that information. It's always, so the other general statement to make here is anytime you can bleed across boundaries that I was talking about factory, but anytime you can bleed across boundaries, then you have an opportunity. And there's boundaries between what is and is not visible to the applications. If you can figure out the right abstraction of that, those channel indices that you could then pass to applications, and now it's application level adaptation.
Exactly.
Yeah,
that's one thing I've been curious about. I've been chatting with a colleague of mine, Kyle Jameson at Princeton, about is you have that kind of information, you can do bandwidth prediction of how much bandwidth the UE is going to get in the next time interval. And if you control the scheduler, you actually know the answer because you're the one computing it. And so it becomes a real opportunity to give the services that are communicating with that UE information that can drive, video quality adaptations, for example.
Yeah. I think one of the challenges here is the really good data is available to the scheduler in the DU. And this is where things start to get a little bit gray and opaque with respect to open source. So there is open source, open air interface has software here, but a lot of the small cells that we are working with, we work with open air interface, but we also work with proprietary small cells. And you don't necessarily get access then to the scheduler. But I think the interface between the DU and the RIC, where these service models are passing aggregations of that data across the boundary, is where there's minimally there's an opportunity to get some pretty good visibility.
There's another question in the chat, Larry, asking about the impact of some of the wireless technologies around millimeter wave and terahertz and so on, and what consequences those advances are going to have for the other.
I didn't quite catch that.
Oh, that what the radio technologies around things like a millimeter wave and terahertz and so on. What kind of impact might those have for the rest of the network?
Oh, for the rest of the network? Well, I guess to me, the scale of IoT devices, the density of the devices, and the very low bandwidth, very low latency bounds that I'm going to have, and the bounds on the jitter of that latency are going to probably require not just delivering it from the radio, but having the edge applications that much closer to the data. So I think The radio changes. I talked very briefly about that. Qualitatively, the change is density, bandwidth, yes, density and the latency bounds. And the only way to meet those, the radio can do a great job of it, but if we don't factor the software stack above that in the right way and move the application, the decision-making piece of the application, that's the other factoring problem, as close as possible to that data, it's not going to matter.
So Larry, I have an out there question, but I guess, oh, go ahead.
No, go ahead. Go ahead.
I have an out there question, and I guess I was thinking, you know, when I first met you, you were doing Planet Labs, so I guess since to think about this kind of question. Ignoring the cellular access network for a moment, one can imagine that new application programming abstractions emerge with Edge Cloud. You're going to have things that code and state that's probably moving around or being partitioned between these different compute units. And you may well want to make things like location and latency, you know, more first-class constructs that the programmer is kind of aware of. So I can kind of think about what that might look like. And, you know, there's ideas in programming languages there's been, you know, a ton of work on people looking at abstractions for mobile computing, very clever formal calculi, and even some kind of practical languages. But then when I start throwing in, you know, the mobile core and the RAN, and I can imagine, you know, jointly programming all of those things, the complexity gets really complicated. You know, it's a little bit, I mean, I can imagine a system architect or a team thinking about slicing and spectrum and frequencies and latency and all of this with, you know, the state and compute for the application. But it just seems like there has to be some, you know, some factoring there. Some, you know, that one team is maybe sort of dealing with something that looks more like a slightly refined cloud model, and one team is thinking about the fabric. But maybe my brain's just too small to think about both those things together. Do you have any? I don't want to put you on the spot and make you predict, but do you have thoughts on kind of where this will go or where it should go?
I mean, you've put your finger, well, two things. One, I love the connection to programming languages. I think whether it's language-based specifically or that line to operating system abstractions and so on, I don't know where the right line is, but I think let me just call them the programming models for building new applications to take advantage of this capability is huge. Just the API that you expose to those applications on connectivity as a service, we don't know what the right answer is. I love the notion that, oh, what are you running on your Edge Cloud? Oh, I've got app A and app B and app C, and I've got a fourth service called it's connectivity as a service. And you can turn the dial on your connectivity to get the behavior out of it you wanted, then you can plug it into this particular app or that app. We have only crude ways of doing that right now. So, and then the second you have those APIs, the factoring comes into play, function placement comes into play. It's all great, but you put your finger on a challenging problem, which is the scale of this thing.
If you go ahead.
Go ahead.
I was just gonna say I'm actually inspired. I've been studying a little bit what's going on with cloud native networking.
Exactly.
Where they've kind of just, I mean, don't quote me, this we're recording, so I need to be careful. Don't quote me on this, but my perception, possibly misinformed, is they've sort of just ignored performance for the most part and start to build the abstractions they want. So they want these very rich, you know, RPC-based abstractions that let applications communicate sort of message stream to message stream, and they want, you know, built-in replication and load balancing and encryption and authentication. And so they just built this kind of amazingly rich, you know, set of communication abstractions that fits what applications want. And okay, now there's some engineering work to make that stuff fast. But I think it's pretty inspiring and kind of cool.
It is. That's kind of where I was going to go. The services as microservices, what do you want to call them? Microservices, services as a first class, you know, abstraction that we are now focused on. It's moving up the stack. It is the new, we could argue it is the new network layer. And there's a huge amount of machinery coming to play. And you're right that it's not terribly optimized. That'll be a whole nother generation of SIGCOMM papers to make it go fast. This is perpetual employment of researchers. But yeah, and they basically have abstracted away all those things you don't want to have to worry about. Security monitoring, the service mesh architecture is exactly that. And I get to focus on my function. The other thing I was going to say is it's hard. I mean, historically, it's been the case that, okay, the mobile core. Yeah, I can see the block diagrams in the standard spec and some literature, but when I get down to it, it's still a big blob of ugliness. But those are being implemented according to cloud native practices now, and the market will force them there. And the second that happens, you will have isolated the key function that I will be able to innovate on. And I won't have to worry about how it scales because that's handled by the database, and I won't have to worry about this and that. And these things will become more localized, I think. It's going to be a game changer as this takes shape.
So
And this was basically the reason we wanted to do this tutorial in the first place. Is this is going to happen. It will happen with or without the SIGCOMM community, but there's a tremendous opportunity, lots of interesting networking / systems problems in here. And we're just hoping that this talented community puts some focus on it. There's lots of problems everywhere, but put some focus on it.
So Larry, there's another question in Slack asking, if the 5G control plane is essentially a service mesh, is there any effort to implement it on top of an actual service mesh?
Yeah, great question. It could be implemented in a service mesh. A service mesh is a framework for taking responsibility for some things that you have to do off your hands, put it in the framework, and then focus on your core functions. The implementation of the mobile core that exists today, that's happening today, does not directly leverage any of the service mesh infrastructure. It could, one could argue it should. We have found that the problem is constrained and limited enough that we didn't need the full power of the service mesh. Yeah, it's a really good question. It's one that we debate internally quite a bit from an engineering point of view, but at this moment, we have recreated the pieces that we needed without going whole lock, stock, and barrel on one of the service mesh frameworks.
So I have a comment to add there, mostly parroting something Oz has mentioned to me before, which is that some of these service mesh platforms have a particular set of interfaces, and some network control functions might need a richer interface than some of these platforms actually offer. And so figuring out what are the extensions or new designs of APIs that would allow the networking constructs we think about to be more naturally represented would be helpful, so that it's not an entirely natural act, I guess, to use.
Yeah, so one of the unfortunate engineering hurdles here is that the 3GPP spec told you how you had to tunnel between microservice A and microservice B, because at the time those were defined, they weren't microservices, and it isn't gRPC. And so there's an interesting thing happening, which is to put some blinders on and say, at these boundaries, I'll speak 3GPP compliantly outward because I have to be interoperable with somebody else's base station and somebody else's whatever. But in this chunk of the mobile core, all bets are off, and I will stop trying to implement the standards because this is my own private gRPC interface. I think that's will be a huge win at the end of the day. Unfortunately, the code right now has a bunch of tunneling expectations baked into it. And literally, I think what I was referring to is we couldn't take some core and just drop it into Google Cloud because the assumptions about the network interfaces being used. But Oz isn't on, so I can say this. I'm pretty irreverent towards the 3GPP spec. In my view, it sort of overprescribes some things. And I think it probably had to be that way historically. But the second this there's going to be a tipping point that we're very close to, that it's now cloud native, and that's just going to get it's going to get swept away. And best practices in cloud native microservices is going to win the day, I think. And then we will minimize, where you had to be backward compatible. Always can come back in and fit that little module on the end if you have to. Are there other questions online? I guess I can go look.
This is a question about security and securing the 5G infrastructure, particularly in the context of fast control loop, application-centric networking, and so on. What does this mean for security?
You can answer that. I mean, that's basically what the pronto work is.
I don't know. I was hoping you'd take it. No, I think there are actually two answers. I think the programmability is a win for security because it's an opportunity to embed security function and improve it as we go along, because the infrastructure is pliable enough that we can actually up our game when the adversaries up their game. And the microservices help also, because the hope is that these microservices are small and bounded, and we can ferret out possible bugs through good testing or even verification, so that we can have more confidence rather than having a big monolithic software stack that's really difficult to verify. But unquestionably, I mean, I worry with programmable data planes that we can write programs that, even if they don't have bugs in that they're not fundamentally incorrect, they may have worst case workloads that really stress the system in ways that reduce their accuracy or put more load on the software control plane. And there, I think there's a lot of important work to be done to understand the impact of, given this P4 program, what's the worst case workload in terms of the stress it's going to put on the system? And I don't think we're particularly strong at knowing how to answer that question yet. So I think there's still more to do to understand adversarial workloads in particular. But I'd be curious, Nate, your take on this too.
Yeah, I completely agree with everything you just said. I guess I'm not a security expert, so I'm not. My home community is not security. But from talking with the folks at DARPA who have funded this work, one theme that emerged was, they're worried about 5G emerging as a monolith that we have no way to understand kind of what's going on. So you could end up with one of these, proprietary integrated solutions, and there could be a kill switch inside. There could be sort of taps that are, giving the ability to snoop on what's going on to the bad guys. And so, I view in the super big picture, this North Star of like, we're going to build a 5G stack based on open source components. That kind of lets us shine a light inside. And so it may not be that every component is perfect or secure, but at least we'll understand, how is the system organized, and in principle, we can drill down as deep as we want to, maybe all the way down to the hardware layer, to understand what's going on. So that's kind of one answer. I guess the other answer, and something that we're doing in this project, is trying to create these kind of some technologies and then products which are sort of hardened diamonds, like the ability to one of our applications we're working on is, the ability to create some kind of slice where we have some way of assuring that the slice is being correctly implemented. The fact that it's isolated from other slices, and the fact that the program that's instantiating that slice is being correctly implemented. So that doesn't completely answer the security story, but if you have this primitive of an isolated slice and you have some reason to trust that that implementation is correct, now you can start to use that as a building block for building other kinds of secure systems. So I guess not to be too flippant here, but I kind of how Larry motivated his whole exploration of this space. I kind of view us as doing a bunch of the work to allow us to take good ideas in how we build systems and how we make them secure, that we've developed over decades, and start to apply them to this area where it hasn't been applied before.
Just to amplify on one thing you said, and there was a question I was just now responding to as you were talking, that it's not just open source. I think you referred to the monolith. I think this aggregation is really, really important. I mean, the 5G or the mobile core 5G, 4G spec is open source. Anyone can read it, anyone can understand it, but it is the monolith of what is getting deployed has been problematic. And it's not just having eyes on the code kind of argument about open source. That's certainly important. But you can't, disaggregation, kind of closing the loop back to closed loop, it gives you an opportunity to understand and have confidence in smaller parts, and then look at the composition problem. And I think that's a really important part of the end-to-end security story. It's when you have these large black boxes in the middle that you really run into problems. Go ahead.
Go ahead, Jen.
Yeah, I was just going to add, I think, developing the software based on cloud principles means that hopefully advances in cloud security become advances in 5G and next G security. And that's a double-edged sword. Obviously, security vulnerabilities in the cloud become vulnerabilities for the wireless network too, but hopefully it's at least on the same trajectory as an entire industry that's focused on making the cloud more secure. And second, this probably is obvious, but just to put a fine point on it, there's tremendous fate sharing on the network now, right? I mean, if you view that a ton of society is going to be relying on next G applications, the network becomes the critical point of failure. And so it makes the security question all the more important because of it's going to be critical to a whole bunch of services and applications that run above it.
Yeah, I was just going to respond to Alan's comment in the Slack about, open source is not necessarily better from a security perspective. And I think, there's been all this stuff in the press around supply chains and, all these open source package management systems, some of the packages have been subverted, and, people have been able to inject code into a huge number of deployed software systems, by putting some code into some node module, or I think SolarWinds was another example where people were kind of getting concerned about these software supply issues. But I guess to present the optimistic view, there's also a bunch of technologies that entities like the Linux Foundation and some researchers have been developing that let you address supply chain concerns. So you could start to build systems that give you a way to get a chain of trust all the way back to the code producer, and maybe you tie that to some kind of identity framework, or simple things like reproducible builds, which let you make sure that the code you're running is the software that the source code that you started from. So it's not like it makes every problem better. There can be new attack surfaces that emerge, but with open source, you have the ability to enhance them to address the security threats that emerge.
So there was another question about on this one on Slack about when you customize and extend functionality, how do you plug that back in? And I think it actually comes back to what we were just talking about, in that these cloud tools are designed to support not only a highly modular system, but a highly modular engineering approach. I often say that what Google, as an example, got right is they understood how to scale engineering, because everything is as loosely coupled as possible, and they have very powerful tools, which now many of them are open source, to plug all the parts back together, test them, integrate them, test them, and deploy them. And it's that I talked about lifecycle management, and I think this is something that's near and dear to my heart. I think those are extremely powerful tools. That it's exactly how you build a system that has pluggable parts to it. You have to get the APIs right, of course, but all of the infrastructure for that is now leveraging best practices, and that's a whole new world for the telco space. But I think it's the important one that we need to take advantage of. Well, we may be winding down, which is fine.
There's one new question in Slack that just went up, Larry. I don't know if you see it now.
Oh, the 5G stack is different than the TCP stack. Oh, I mentioned that. Yeah. Well, so it's not specifically RAN. I think the SDN stack is different than the TCP/IP stack, and it's a different factoring of the. It's not about protocols anymore, because I can ship you the code that you run on your side and I run on my side, and we write the little filter that runs in between us, and we load it into a switch. And So the protocol interoperability game has completely changed because of that. And so it's, in my view, what I was alluding to when that throwaway comment earlier on in the tutorial was, I think it's the SDN stack that is a big one. And then trying to apply it to the use case of RAN. And right now we're sort of in the first stages of that, but I think it maps onto RAN as well as it maps onto wireline. Yeah, so that's the stack. I would hope starts to become a more dominant way of organizing and teaching networking classes, but that's still to happen. You still have in-host, they still run TCP/IP, that's great. It's still important, but down in the substrate, it's the SDN stack. Okay, well, hopefully this was helpful. If you have lots of material to take a look at, you should be able to find multiple ways of getting a hold of me or us if you have further questions or have trouble finding something. Like I said, there's a ton of software. There's programming, hands-on programming available. And I think there's some interesting opportunities. I'm hoping to see future SIGCOMMs take advantage of this opportunity. Jen, Nate, any other closing thoughts?
I think it's an exciting area, and I think the book and this tutorial are a great opportunity for us to start getting up to speed as a community and learning by doing.
Learning by doing, yep. All right, well, thanks everyone, and have a great rest of your week at SIGCOMM. Bye.
Bye, everyone.